The year is 2030. A crew arrives on the moon, while on Earth, growing energy and climate crises threaten to spin out of control. The crew's mission is to test a new mining machine designed to extract a precious resource from the lunar soil and bring it back to Earth. If the machine can collect enough of this rare element, it could power a new type of energy production on Earth, one that doesn't produce any greenhouse gases or radioactive waste. The fate of the world economy and the health of the planet rest in the balance as the crew returns with its precious cargo. This is just one way that our lives may be transformed if mankind can tackle the enormous challenge of mining the moon. 239,000 miles away sits Earth's only natural satellite, the Moon. Formed billions of years ago, it has remained a constant presence from the beginning of humankind. But what appears as a lifeless rock in the night sky might be an untapped treasure trove of resources.
100 years ago, when you were to think of the tundra, you had this vision of a bleak, desolate, a useless piece of real estate. Now we realize that the tundra could be some of the most valuable real estate on the planet Earth. Our impression of the moon may also change in the same way.
The moon has been victim to billions of years of asteroids, micrometeoroids, solar winds, and cosmic rays bombarding its surface.
They're constantly bombarding the surface at very, very high velocities, maybe as much as 20 times the speed of a bullet, and breaking up the rocks into a very, very fine-grained material.
These microscopic collisions are so intense, the surface is melted upon impact, embedding particles into the lunar soil, which is called regolith.
Whatever the sun is spewing out is going to hit the moon, and some of it's going to stay there. And that's what's interesting in terms of resources, because most of what comes out of the sun is hydrogen, about 4% is helium, and it is being embedded in the minerals and the glasses and the dust of the moon continuously.
These gases, trapped in the regolith, are the precious resources that moon mining experts are after. Harvesting these gases could save space crews from having to bring these types of essential supplies from Earth. That's one of the keys to making a permanent lunar colony a reality. But there's more. The moon may hold the solution to all of the Earth's energy problems. One man who believes in this incredible possibility is Dr. Harrison Schmitt. In 1972, he was the only geologist to ever visit the moon.
I was assigned to the last mission to go to the moon, Apollo 17.
He, along with other Apollo program astronauts, scoured different regions of the moon and brought back 842 pounds of regolith and lunar rocks to study on Earth.
The rocks are very much like Earth's rocks in many senses, but they are very distinctly lunar, and the soil is very, very different from anything we've seen on Earth.
The gas that has Dr. Schmitt and his colleagues at the University of Wisconsin at Madison so excited is a light isotope of helium called helium-3. It's a type of helium that has one less neutron than the typical helium-4 that we use to fill balloons here on Earth. So what's so great about helium-3?
It is a nearly ideal fuel for fusion power.
Imagine a powerful form of energy that doesn't produce any greenhouse gases or radioactive waste. That's what's great about using helium-3 for fusion power. Unlike Earth, where the atmosphere filters out most of the harmful UV rays and other particles from the sun, including helium-3, the moon has no atmosphere to protect its surface. After 4 billion years of solar particles pounding the lunar soil, Schmitt and his colleagues believe there's enough helium-3 stuck in the regolith to make it worth extracting it and bringing it back to Earth.
Helium-3 is the holy grail of the fusion process. Fusion is what makes the night sky light up. It's the secret of the stars.
Using helium-3 for fusion power is enticing because it offers major advantages over dirty fossil fuels and today's nuclear fission power plants. First of all, helium-3 fusion is a lot more efficient than fission power. Fission reactions produce heat, which is then used to turn water into steam. Then that steam drives turbines to produce electricity. And since no process is 100% efficient, energy is lost at each step. But helium-3 fusion skips the heat and gets right down to business.
It produces a proton when it fuses, and those protons can be converted directly to electricity. You don't have to lose efficiency by going through what's called a heat cycle.
A second advantage for helium-3 fusion is that it's a clean process. Nuclear fission and other types of fusion create a dangerous byproduct, radioactive waste. The reason for these big differences can be found inside the tiny atomic structure of the fuels. Splitting atoms with fission produces radioactive neutrons, but H3 fusion produces non-radioactive protons that are converted directly into electricity.
And that is what potentially not only makes major commercial sense and environmental sense for us here on Earth to have a very clean fusion fuel to use here on Earth as a partial alternative to fossil fuels.
Just 220 pounds of helium-3 brought back to Earth could power an entire 1,000 megawatt fusion power plant for a year. That's enough energy to power a city like Dallas, Texas. But producing helium-3 on the moon would be no small feat. There's far more helium-3 on the moon than on Earth. But there's still only 20 parts per billion in the lunar soil. That means sifting through 3/4 of a square mile, the size of 400 football fields, and 9 feet deep, to create 220 pounds of fuel. And so far, nobody has invented a machine that can come anywhere close to collecting that much soil and processing it into fuel.
A colleague of mine equated mining helium-3 to trying to get gold out of the ocean water. There is gold in ocean seawater on the order of a couple parts per billion. Nobody has figured out an economical way of extracting the gold from ocean water.
Another huge hurdle is that the only way helium-3 is useful is if it's returned back to Earth. Shipping oil around the world in a tanker costs a few $100,000. But bringing helium-3 back from the moon on a spacecraft is estimated to be hundreds of millions of dollars. Until these huge issues of transportation and excavation are solved, it seems highly unlikely anyone would bother to mine helium-3 and build a fusion power plant. It appears that the only way helium-3 has a chance of becoming cost-effective is if lunar mining technology and infrastructure is developed for other reasons first. In fact, NASA is exploring ways to build a colony on the moon.
At first, it seemed impossible, preposterous to take barren moon rock, devoid of water, devoid of resources, and from that, perhaps create a Garden of Eden. But yes, it is actually possible.
But first, scientists must start with the very basics. NASA needs a machine capable of excavating the lunar soil. And one way of finding this revolutionary new machine is a fun and innovative competition that NASA takes part in. It's called the Regolith Excavation Challenge. For 2 years, teams have been invited from all over the world to bring their original lunar excavator inventions to compete for first prize, a cool $500,000. Today, 10 teams have come to the Cal Poly campus in San Luis Obispo, California to join the competition. Students,
thank you very much,
engineers, even toy makers.
Do you want to ride it? I haven't really got to No, just kidding, you can't ride it.
Are here to see if their unique designs can deliver the goods and take home the prize. The rules seem simple. The excavators have to work autonomously, just as if they were alone on the lunar surface. Each team has 30 minutes to excavate and deliver 150 kilograms of simulated regolith from a 169 square foot area into a hopper. The simulated lunar soil is a fine sand-like material made from crushed volcanic rock. The competitors wear masks to keep the powder out of their lungs. And most important of all, the last rule is that teams only have one chance to compete.
Last year, one guy said, just let me in there. I can change one variable, it'll work. Sorry, you're on the moon, you can't do it.
As the first team approaches the area nicknamed the Sandbox and loads their excavator, it's clear this isn't child's play. This excavator can't find its way to the ramp. It's just one of many challenges that teams will face today. A lunar excavator is one of many new pieces of special equipment NASA will have to build for a sustainable lunar colony on the moon. And the first requirement for any type of equipment will be surviving in the harsh lunar environment. Building a colony here will expose humans to some of the worst the universe has to offer. Someday, helium-3, a rare element that may exist in great enough quantities to mine on the moon, could prove to be the energy source that frees the world from fossil fuels and radioactive nuclear fission. But that's the pot of gold at the end of the rainbow. First, NASA has to be able to settle a permanent lunar colony. That means figuring out how to sustain life in a place that is completely inhospitable. NASA's program to return to the moon is called ISRU, or In Situ Resource Utilization.
We commonly call it living off the land.
At first glance, it doesn't seem like a viable colony could spring up on the lunar surface. But humans have created colonies in inhospitable environments on Earth before. Some have even thrived.
Let's look at it this way. Las Vegas was built in a desert that had no other qualities other than it was there. And, you know, they built it and look at it now. But it was really just a desert. It was the imagination, the creativity of the people that founded and built Las Vegas that turned it into a place of value.
In the desert, temperatures rise to unbearable levels in the day and plunge at night. There's no food or shelter from the elements. Without protection, humans don't survive very long here. But Earth's atmosphere does protect humans from the most extreme conditions of space. On the moon, where there is no atmosphere, the dangers are far more severe. The mercury soars to 250 degrees Fahrenheit in the day and plunges to negative 250 degrees at night. A small tear in a spacesuit will expose a colonist to the vacuum of space. Another danger comes from solar flares, which can unexpectedly leap off the sun and blast the surface of the moon. Colonists will only have a matter of minutes to find shelter or die from the intense dose of radiation. The only way to survive on the moon is if colonists are protected from these unpredictable conditions. And there's one natural wonder here on Earth that might provide NASA with some inspiration: lava tubes. The big island of Hawaii is dominated by two massive volcanoes, Mauna Kea and Mauna Loa, and nearby Kilauea still shows her rage, spewing lava up to the surface. Lava tubes are the result of a volcanic explosion of hot lava. These explosions are so powerful that lava surges through bedrock, melting what was once solid rock and creating a path for new lava to flow. The Thurston lava tube, which scientists estimate was formed about 350 to 500 years ago, extends 38 miles and is sometimes 30 feet wide.
This lava tube is about 200 and 250 feet in length, and if this was on the moon, the thickness would provide us with adequate protection from the cosmic rays. Okay, you can see that the lava tubes aren't uniform dimensions. This is pretty typical of lava tubes in general. Lava tubes aren't uniform in size or shape because that's just the way nature is. Nature isn't perfect. You get larger antechambers above and below, and you can see in the tube system there are different stands of lava.
But what do lava tubes have to do with lunar colonies? The lunar regolith is great at absorbing dangerous solar and cosmic radiation. And there is evidence the moon has ancient lava tubes winding just below its surface. These subsurface and collapse tubes that have formed natural trenches on the surface of the moon could provide a safe haven for colonists.
Protecting the crews from that harsh radiation environment is important. One of the concepts there is to bury the habitats in either lava tubes or actually using the soil, the regolith, to bag and put over those habitats to provide that radiation protection.
Building something underground wouldn't be as difficult as it sounds. NASA has already had great success with inflatable habitats surviving in extreme conditions like the Antarctic.
Inflatable habitats are comprised of multi-layers of fabric that we pressurize and they expand and then rigidize to provide a rigid structure for the crew to live in.
These inflatable habitats might be the seeds that allow the moon to grow into a whole new world.
These first outposts that we send are going to be a couple of construction shacks and little habitats, and then we can use that to start building more infrastructure, and other countries will show up and bring their pieces of hardware. And so to a certain extent, you're going to have this multicultural New York City where you have, different languages and different people, commerce coming back and forth. That, I think, is an exciting future.
The story of civilization is a story of human beings going into new places, harvesting the resources, creating new industries and new commerce. It's worked here on Earth throughout our history. There's no reason it shouldn't work on the moon.
But providing safe habitats is just one of many hurdles NASA must face head-on before any colonist considers a move to the moon. They also need to pick a location where colonists can truly live off the land, and that means being as close as they can to resources. Like gold miners searching out their fortunes in California, scientists must first do some prospecting on site to find an appropriate place to mine. Choosing the wrong location could make the difference between life and death for the colonists. Miners on Earth know all about taking gambles to discover a jackpot of resources buried in the ground. They always follow 3 key steps to achieve success.
One is prospecting, which is finding the resources, location, quantities, and exactly what we're looking for. Excavation, which is the process of digging the mineral, the ore, where those resources are found. And finally, extracting those elements or those materials that we're interested in having.
Mining on the moon will also involve these same 3 steps: prospecting, excavating, and extracting resources. But the execution is far more complex than any production on Earth.
Currently, there's no mining technology that is ideally suited for the moon. You cannot use ordinary kinds of welding equipment. You cannot use internal combustion engines. Gasoline don't cut it on the moon. We have to have oxygen in order to get that reaction going. On the moon, there is no air to energize our machines.
We know the lunar environment is deadly to humans, but it is also incredibly hard on machines. Equipment can be crippled by the extreme variations in heat. The vacuum of space wears on joints, causing leaks. The lack of humidity means static charges can build up to dangerous levels. And the lunar soil is extremely fine and abrasive. Exposing electronics to the regolith can render a machine completely useless after a short period of time. But if NASA can learn how to overcome these obstacles, then the possibility of a lunar mining community might become a reality.
Setting up an operating, self-sufficient, permanent lunar base on the moon may be comparable to building the pyramids.
Despite the enormity of the challenge, the payoff could be just as big. Scientists think that trapped in the lunar soil are gases that make up the basic necessities of life. Lunar samples brought back from the moon's equator during the Apollo era revealed that oxygen, helium, and hydrogen released by the sun had become embedded in the soil. But NASA's sampling only represented a very small area of the moon's surface. In the 1990s, 2 satellites, Clementine and the Lunar Prospector, remotely investigated most of the lunar surface. Spectroscopic analysis revealed that oxygen may exist everywhere on the moon's surface. An astounding 40% of the regolith contains oxygen-rich compounds. and there might be a vast amount of hydrogen and possibly even water ice at the polar regions. But scientists can't be sure what's really there until they return to the moon and get their hands on more soil samples to confirm the remote satellite observations. Maybe Scarab, Carnegie Mellon University's lunar prospector prototype, will be able to deliver the goods. Back at NASA's Regolith Excavation Challenge, the search continues for a prototype that is smart enough to mine the moon on its own and sturdy enough to dig a lot of lunar dirt, known as regolith. The home team, the Cal Poly Slobotics, is learning the hard way that designing a robot that can move autonomously through the simulated lunar soil sandbox is not easy.
Sorry guys, most boring robot ever.
The judges don't have much sympathy for the teams.
This is rocket science, and this is the kind of thing that the NASA and a lot of companies, a lot of universities and organizations like JPL do all the time. And it's easy to make it look simple, to see this little rover roll off this spacecraft that bounces around and lands on Mars. It's incredibly difficult.
Several more teams still have a shot at making this difficult task look easy. There's no doubt that autonomy is incredibly important for any robot that's going to go prospecting on the moon. The moon is covered by miles of rocky passes and uneven trenches. Plus, astronauts won't even be able to survive the extreme conditions where NASA plans to send the first autonomous prospectors. NASA has chosen to go to the polar craters of the moon as their first prospecting site to search for resources. Never before explored, some of these craters are as deep and as wide as the Grand Canyon. They are so deep, they are masked in permanent darkness, and the temperature averages minus 374 degrees Fahrenheit.
Because they never see sunlight and they see deep space, they are approximately about 40 degrees Kelvin above absolute zero. Absolute zero is nothing moves. Molecules don't move. So it's extremely cold.
So why does NASA want to start prospecting in a place where the degree of difficulty is off the charts? Because remote satellite analysis shows that those dark craters may also contain a lot of hydrogen, the main ingredient in rocket fuel. And there's also a chance of finding the grand prize of lunar resources, water in the form of ice.
We forget that comets are made out of ice. They're dirty icebergs floating in outer space, and every once in a while, over billions of years, they collide with the moon.
Water would be the greatest discovery NASA could hope for. Not only would they have water to drink, they could also separate the oxygen and hydrogen molecules, so they'd have oxygen to breathe and use the hydrogen for rocket fuel. That could turn a simple lunar mining colony into a multi-purpose fueling depot, launching crews deeper into space than ever before. While the idea of using lunar water ice is exciting, the reality of prospecting for it, then excavating and extracting it, is one of the greatest technical challenges of all time. But that hasn't scared off the engineers at the Field Robotics Center of Carnegie Mellon University. NASA has turned to them for a lunar prospector because this team has a knack for designing one-of-a-kind robots that have already proven themselves in extreme conditions.
This is the high bay of the Field Robotics Center, and over the last 20 years, we've built a number of different robots for exploration. Some we've retired, like Hyperion, which we used in polar regions. Zoe, we've been searching for life in Chile. We've built robots to operate in underground mines, Groundhog and Cave Crawler.
Scarab might be their next great achievement if it can successfully roam the moon's deep, dark craters for a long period of time and sample lots of different areas looking for water and precious gases, also known as volatiles.
Scarab as a prospector on the moon is intended to be an early explorer to look in places in craters and try to measure the amount of minerals and volatiles like water and oxygen that might be in that soil.
Operating in darkness is a major issue. Most man-made objects in space use solar power, but the polar craters are so deep, sunlight can't reach the lower sections. So Scarab is powered by a radioisotope. This mini nuclear engine keeps things humming. It will provide up to 100 watts of energy, only enough to power a light bulb. But with only 100 watts of power, Scarab still needs to be sturdy enough to drill 3 feet into the frozen soil of the craters. So the chassis must weigh in at 550 pounds to provide enough heft to counter the moon's reduced gravity and the torque forces created by drilling into the tough soil.
Scarab is a drill-centric design. Literally, the drill is in the center of the robot. The robot is designed to be able to slowly drive this drill into this very dry, very cold material.
But perhaps Scarab's coolest feature is its ability to get from one dark, rocky drilling site to another autonomously.
With Scarab, we use laser scanners to model the terrain and build topographic models. And then the robot itself can interpret those models to determine where to drive.
It also rides on some specially designed wheels, since one flat tire could sink the whole mission. They're called Tweels.
There's no inner tube, there's no pneumatic, there's no air inside it. It's got a stiff band with the tread on it, and then these flexible spokes. Why this is important is that on the moon, we don't want to use tires that are filled with air. And we also, on the moon, don't want to use tires that are going to get stiff when they get cold.
Is Scarab up to the challenge? It appears it has been designed to deal with every environmental extreme the moon can throw at it. But first, it's got to prove itself to the team at NASA. And that means passing a future field test on Hawaii's Mauna Kea volcano, in terrain that's similar to that of the moon. Failure on Mauna Kea might send Scarab's designers back to the drawing board. Hundreds of miles away at Kennedy Space Center in Florida, its critical payload, called Resolve, is being prepared for its own big test.
It's a multi-purpose experiment that's designed to not only look for water ice, perhaps in the permanently shattered craters of the moon, but also test the ability to make oxygen from the regolith of the moon.
Resolve is a nuclear-powered oven that is designed to heat up the core samples delivered by Scarab's drill to release gases, also known as volatiles, of different elements in the soil, like oxygen or hydrogen.
We drill down about 1 meter and take a core sample. We come up, dump a portion of that into a crusher to crush it down to a fine size. Then we heat it to about 150 degrees C and look for volatiles as they're released.
If Resolve detects volatiles like oxygen or hydrogen in the frozen soil, a whole new world may open up on the moon. The moon might become a great center of commerce, an intergalactic port of activity where both public and private industry can thrive.
You're making a case for building the infrastructure that can keep you on the moon. Here we are at a port, for example. And in this port, there are container ships carrying things in and out that are going to all kinds of places. There are government activities underway here, there are private activities underway, there's transportation, gambling ships and cruise ships coming in and out. All of these things combine to create a viable economic argument for this port to exist. The same thing can happen on the moon.
But before the moon can turn into a bustling spaceport, NASA first needs to execute 2 more steps in the mining process: the excavation and extraction of resources. And looking to surface mines here on Earth might hold the answers for successfully mining the moon.
When you're talking about large-scale processing for lunar colonies, then you need to look at the Earth mining situation a lot more, especially surface mining.
Looking out to an open-pit surface mine on Earth, space engineer Angel Abud Madrid can easily see the similarities and differences when mining here and on the moon. He, along with the scientists at the Colorado School of Mines, are experts at large-scale mining techniques.
This open pit surface mining operations on Earth resembles what will take place on a large crater on the moon. Contrary to what we see here, layers upon layers of the mountain being excavated with large equipment, on the moon we're going to have a very compact operation. The bucket ladder is the next generation technology in terms of lunar excavators.
At first glance, lunar excavator prototypes might seem completely ridiculous compared to Earth-size excavators. But the realities of the lunar environment make a small, slow-moving bucket ladder design a perfect choice to handle the regolith.
You have a bucket, much larger area, that collects the dirt, and then it's transported to the top of the arm where it dumps the soil into the collection bin. Once the soil is dumped into the collection bin, it opens up and dumps it into the extraction plant.
Unlike Earth-based surface machines that dig deep into the ground, lunar excavators will have to skim the surface of the regolith, where the highest concentration of particles from cosmic rays, solar winds, and micrometeoroids have embedded into the soil. And these excavators must be specially designed to handle regolith, because regolith is not like soil on Earth. It looks and feels like microscopic shards of glass. Its dust is finer than talcum powder, and when disturbed, it will take longer to settle on the ground, since the moon's gravity is just 1/6 that of Earth's.
It's not like walking on a sandy beach. This is walking on very fine broken glass, which is going to make the operation of excavation and mining on the moon a very difficult task.
Well, it's not like you're just scooping up sand. You have to actually cut into the material. And actually on the surface of the moon, it gets more and more densely packed as you go down onto the surface. So you have to dig that much harder. Even though it's loose material, it's like digging into ice or rock.
And if current estimates prove to be accurate, excavating enough regolith to find a few molecules of valuable resources means scooping up an area about the size of a basketball court. And even if someone develops an excavator that can scoop up tons of regolith day and night in the tough lunar environment, there's still one more step in the mining process, and it's the most critical one of all: extraction. In a high-security lab in Colorado, one team believes they've come up with a machine that will solve all of NASA's critical excavating and extracting needs for mining the moon. Scientists at Lockheed Martin's Space Technology Lab are getting ready to unveil for the first time a system that they say will not only excavate large amounts of regolith, but also extract life-supporting oxygen. Their revolutionary prototype is called Pilot. Pilot is a one-stop shop for oxygen production that will arrive on its own platform.
The whole thing will be self-contained, so we'll actually have the robotic excavator itself on this. We'll drop it onto the ground, and it'll go around and collect the soil, bring it back to be processed by the production plant.
What makes Pilot a perfect fit for lunar colonies is that it will have the ability to land anywhere on the moon autonomously, going to any site where prospecting equipment has shown high levels of oxygen or water trapped in the lunar soil. Pilot's excavator component uses a bucket wheel design. It slices and dices the tough regolith with a series of small blades. The blades slowly feed the regolith into an enclosed bucket to avoid creating troublesome dust. Once loaded, the excavator returns to the lander, delivering lunar soil into a hopper. Then, the all-important oxygen extraction step begins.
Take soil, lift it up in this bucket. It would be pulled into the reactor through this auger. The auger then delivers the material inside the reactor, which is in this vacuum vessel.
High heat breaks the molecular bonds that hold different elements in the regolith together.
All right. There we go.
Hey, that's cool.
The vacuum vessel then rotates with the soil inside it. You heat it up to 1,000 degrees C, and it combines with hydrogen, and it makes water. Those gases are circulated in these pumps and these tanks, and then condensed over on this side of the reactor.
Creating water helps pull the oxygen out of the soil, and obviously, the colonists can use the water if needed. But Pilot's main function is to separate the hydrogen and oxygen again in order to capture the oxygen for breathing. Then, the hydrogen is recycled so it can help to pull more and more oxygen out of each batch of regolith.
This plant makes enough oxygen to provide all the needs for an astronaut, which is about 1 kilogram a day.
Pilot definitely holds a lot of promise in making lunar colonies a reality. But before Pilot or any piece of hardware is commissioned to head to the moon, it needs to pass the ultimate field test. Mauna Kea has not erupted for 4,000 years, but evidence of its destruction is everywhere. The terrain is littered with rocks and rubble spewed from the volcanic explosions. Some explosions were so powerful, they sent lava thousands of feet into the air, creating lava bombs.
This is a lava bomb. This thing went almost suborbital.
Like Earth, the moon was also volcanically active, but billions of years ago.
The dark regions that you see, the mare, are really lava fields that have flown out from the moon when it was hot. And so that's what we have here in Hawaii.
It's a unique type of soil only volcanoes can create.
It's amazing how fine all of this is. In other places we go, there's pebbles, but this is all very, very fine and extremely dry. Very little organic matter, too.
In August 2008, the NASA team scoured the volcano to choose sites for their grueling field tests of lunar mining equipment. If they can prove themselves here, Scarab, Pilot, or Resolve might make history and be the first machines to mine the moon. At 10,000 feet, rocky plains, deep craters, and volcanic ash all combine to create the perfect lunar mining obstacle course.
And so both the combination of the terrain aspect as well as the material definitely suits our needs for this particular test.
The scales here just still amaze me. You turn around and look and, you know, it's just as far down there as you guys were down the slope when we were over in the crater.
This challenging terrain is exactly what NASA needs to push their technology to the limits and fine-tune designs for the moon.
There's a lot of reasons why we would want to try to do the things that we're doing here. One of them is the hardware, and push it to the limits, find out what it can do and what it can't do. It's still very prototype hardware.
November 2008, a larger team has returned with the mining prototypes and other kinds of potential equipment for the moon. It's make or break time for Pilot, Resolve, and Scarab. As the field tests begin, wind renders some machines useless. But Pilot is able to collect dirt and process it, and Scarab is able to maneuver the rough terrain and steep craters, with its wheels successfully carrying Resolve. As the team finishes, they are encouraged by the results. If the prototypes can consistently manage this tough terrain, they just might have what it takes to survive the lunar environment. But perhaps the biggest problem NASA faces is simply getting back to the moon in the first place. It's reaching the end of the day at the Regolith Excavation Challenge, and the experimental mining machines are having a hard time getting any traction on the simulated lunar surface.
3, 2, 1, start.
The texture of the simulant and navigating around rock formations are obstacles teams can't seem to overcome.
Oh well. It does some pretty good dirt, though. The problem with going to space is you never have that second chance. When we went to Mars and succeeded this last time, it was only because we simulated the landing of it literally thousands of times, including every conceivable problem.
In fact, as the 10th and final team of the day tries to see if their prototype has what it takes to mine the moon, like all of the other teams, their machine fails in the seemingly simple task of delivering simulated lunar soil to the hopper.
This is a big prize.
Yes, it's a big prize.
$500,000 on the line for the winner. And these teams have worked hard, but they came up short.
It's a stark reminder of the many hurdles to overcome in order to prospect, excavate, and extract resources on the moon. Establishing a permanent lunar colony is as daunting and complex a challenge as any mission in the history of space exploration.
At the present time, we do not have the technology necessary to live off the land of another alien world. However, it's coming, and it's coming very fast.
Even the basics we take for granted on Earth, Roads, excavators, supplies, living quarters become impossibly hard to create when planning for the moon. But if mankind can overcome these obstacles, a revolutionary new opportunity will be born. A sustainable lunar colony could exist in space where colonists could live off the land. And that colony could grow into a permanent lunar city where galactic travelers could stop and collect goods for travels into deep space.
Therefore, the moon becomes the gas station and the supply depot throughout the solar system.
It may even solve the world's energy problems by providing a ready source of helium-3 to power truly clean energy plants on Earth. But it all starts with working hardware and a way to get there. With the space shuttle ready to be retired, NASA is racing to finish a new rocket that can return humans to the surface of the moon.
Constellation is America's program of returning humans beyond low Earth orbit to the moon and eventually to destinations such as Mars. The Constellation program is much more robust than what we did in the Apollo days. Our objectives are to explore the moon globally, which means we need much larger rockets and much larger spacecraft in order to conduct those missions.
NASA's new exploration program involves 2 new rockets. Ares 1 is a more compact rocket meant to carry humans to and from the moon. Ares 5 is its complement, a heavy lift rocket with the space to carry excavators and other lunar mining materials. But going to different parts of the moon means that the landers may not always have a flat surface to touch down.
Landing on the moon poses a very significant risk. We need to avoid things like craters, boulders out that will be out on the surface. So avoiding the craters and the boulders is important. We also need to keep in consideration where the outpost will be. For instance, as the landers land, they will kick up dust and rocks, and we've got to make sure that the outpost is sufficiently far enough away that they won't be damaged.
This new generation of rockets will usher in an entirely new era of exploration, both on the moon and beyond.
One of the objectives of going to the moon is for scientific and economic expansion reasons, but it's also to explore ways in which we will eventually use to go to Mars.
Mining the moon is the key to establishing and expanding a lunar colony. But like a city rising out of the desert, or a small harbor growing into a bustling port, it has to make economic sense.
If NASA's going to go back to the moon and make it viable, we have to create an industrial infrastructure that is profitable for as many sectors of our economy as possible between here and the moon.
The desire is there, and the vision. It's a dream that becomes closer to reality with every generation.
This concept of mining the moon, which was very futuristic just a few decades ago, it's finally coming to reality.
Another reality is that this new mission to return to the moon has energized scientists like no other task in 40 years.
It's the chance to try something completely new that NASA or anybody else, for that matter, has ever done before. It's something that can make a difference to how we explore the moon and Mars. And it's something that I think resonates with the American people. The idea of pioneering is built into our culture.
I think it's inevitable that there'll be exploration and assessment of the resources on the moon, and we'll find ways to use those resources so that we can establish the lunar bases and then move beyond the moon to the planets.